Now we want to run a test where the population standard deviation sigma is unknown. This will be a t-test. The t-test Excel commands are a bit more complicated as far as what you actually type in, instead of doing something different at the end based on right-tailed, left-tailed, or two-tailed. How you actually input it into Excel is different. The first thing also that's different about these is that they require a quote DF input, which stands for degrees of freedom. This value is always defined by n minus 1. So if you know your sample size n, you just subtract 1 from that, and that's what you put in for your degrees of freedom. You will use equals t.dist if you're running a left-tailed test. And when you input there, you have to put in your t-value, degrees of freedom, and a 1. When you use, or if you're running a right-tailed test, you will use equals t.dist.rt for right-tailed. That only requires the t and the degrees of freedom. And if you are running a two-tailed test, you're going to use enters t.dist. That's supposed to be a dot. Let me fix that typo. This should be a dot, a period, not a hyphen. t.dist.2t. And inside there, you put the absolute value of t, which just means whatever t is, put it in as a positive, put your degrees of freedom. Okay, so again, use this template, use your Word document that has these formulas in there for you as you're working on these. I am not going to do an example of every single one of these. I'm going to do one example, and they will all work the same way, just with that difference of what you actually type in Excel at that moment. So for our example, we are going to revisit our prior problem about the flights delayed per month. So this is also in that installs and delays data set, with the second tab being the delays. These were number of delayed flights in a certain month at some airports. It says, we are told, and we knew this from our prior question as well, that the population of delayed flights is normally distributed. We have this 20 sample data set. So what that tells me right now is my n value. That n is 20. And it says that it has been accepted in the past that the mean number of delayed flights per month is 300. So that's going to lead us to our null hypothesis. This is what we've been told that it has been in the past. But we want to test whether that has changed. So that's going to lead us to our alternate. And we're going to perform this hypothesis test this time with an alpha value of 0.01. And I chose the alpha values for these two examples in this section specifically based on the confidence levels that we did in our confidence interval section. In the prior problem, we had a confidence interval of 95%. And remember that confidence levels and alpha values are always complements of each other. So that's why I chose an alpha of 0.05 on that one, because 95% and 0.05, those are complements. On this one, when we made the confidence interval before, we did a 99% interval. So the alpha value of 0.01 goes along with that. That's its complementary alpha value. Why do we have to run a t-test here? Well, if you look into the information that we're given, we do not know the sigma value. So sigma is unknown. Right? They don't tell us anything about this population's standard deviation. So when that's missing, we have to automatically do a t-test. Write our null and our alternate and decide, is this a one or a two-tailed t-test? So I'm going to write H sub naught and H sub A. And we have been told that the mean, the accepted value in the past of the mean number of delayed flights per month was 300. So that's our null, that mu is equal to 300. And we are hypothesizing that it has changed from 300. So mu not equal to 300. We have no direction on this one. We do not care that it has went up or down. We're just saying, has it changed at all from 300? So a two-tailed test in this case. Find the sample mean, x bar, and the sample standard deviation, s. Okay, because again, we do not have that sigma value, so we need to calculate the s value and use that instead. So in order to find x bar, we're going to use the equals average command. And to find s, we're going to use the equals stdev.s command on this data, specifying that it is in fact a sample that we're working with here. So I'm going to go over to my Excel. I'm going to, next to my x bar, put equals average, and then highlight my data set and click enter. So it looks like our average is 315.75. And our sample standard deviation is equals stdev.s. Highlight the data set. So it looks like our sample standard deviation, I'm going to keep 3 decimal places here, 51.728. That's what we need from our data set. The next information actually is going to come from the question. So we have to identify the mu sub 0 and the n. So we can do that now. Mu sub 0 is that hypothesized about mean, so 300. And n is the sample size. We already decided that was 20. With that information, we can compute the t-test statistic, where everything is the same as calculating a z, except we just use s in place of the sigma since we do not know sigma. In this case, we'll have t equals 315.75 minus 300 over the quantity, I'm going to put parentheses around it, of s, which is 51.728 over the square root of 20. I can calculate that top part in my head. That's just 15.75, but the division I need some help with. So I'm going to go over to my calculator and type in 15.75 divided by parentheses, and inside of the parentheses, 51.728 over square root of 20. Close that up. Looks like my t-test statistic comes out as 1.362. Right, and now I'm ready to go into Excel to actually find this p-value. We're going to use, because it's a two-tailed test, the equals t.dis.2t command. And if we remember from what we were told, what that accepts is the absolute value of t and the degrees of freedom. So in our case, the t-value already was positive, so I don't need to change that at all. But I do need to think about what is my degrees of freedom. Degrees of freedom is always n minus 1. So in this case, it's 20 minus 1, or 19 is what we're going to put in there. So p equals t.dist.2t. And inside of there, we put in the absolute value of the t, so 1.362, comma, the degrees of freedom of 19. So I'm going to go ahead and minimize my calculator. I'm going to go back, I'm going to go over, I'm going to skip maybe a line or two. So the p-value is equals t dot, notice what comes up, my 3 options come up, so I choose the correct one. And remember that it even gives you the tip or reminder of how you have to enter this in. So we're going to enter in 1.362, comma 19. Looks like our p-value then is about 0.189. That's what I'm going to keep. I'm going to call this 0.189. Now the rest of this we can do on our own. So we compare p to alpha and draw the conclusion. So our p-value was 0.189, and how does that compare to the alpha value of 0.01? It's much larger. It's greater than in this case. So my final conclusion might be something like, since p is greater than alpha, we fail to reject the null. Larger p-value, longer sentence. So we're going to fail to reject the null. What that means in context is that there is not enough evidence to conclude that the mean number of delayed flights per month has changed from 300. So remember again, I have to watch my wording. I just don't have enough evidence that it has changed. Maybe it has changed. Maybe if I took a bigger sample than 20, maybe if I did this again, maybe I would find evidence. But as of right now, in this very moment, I just don't have enough evidence to say it's changed. Doesn't mean I fully, wholeheartedly believe that it is still 300, but I can't change my mind. I haven't provided enough evidence. So we have to stick with the 300 value, but I wouldn't use the word prove. I haven't proven that it's 300 without a shadow of a doubt. I failed to provide any evidence that it's anything other than that, though. So I would just stick with something like this, that we failed in our endeavor of trying to provide evidence that it has changed.